beautiful, beautiful, absolutely gorgeous. Right here in central Utah, we're along this hinge line. We're on the very edge of the, what we call the shoreline of the Antler Basin. You go farther to the east, it all becomes carbonate. So all the Mississippian rocks east of here are all Mississippian carbonates. But from here westward, you start picking up shales. As you go farther west toward Nevada, you start picking up some sandstones, which are excellent reservoir rocks. You go farther west, you pick up very, very thick sandstones interbedded with the shales. Then time you get over to the Diamond Range, where we got conglomerates, we got sandstones, and we got shales. And the organic material increases westward until you get way over onto the Antler Mountains, and then once you get there, then the organic material drops off once you get up out of the Portland Basin. But about where the Diamond Range is where the rocks are the very richest and the thickest. So we got richer source rocks and richer and better reservoir rocks out in Nevada than we do here in central Utah. What we're looking at for the main target in Nevada is the Devonian carbonates thrust over the top of the Mississippian source rocks. And in Nevada, it's already been proven we've got a very prolific oil production out of those karsted Devonian carbonates, up to 4,000 barrels a day. In contrast with a Wolverine deposit, they're only getting 400 or 500 barrels a day. Now we've got a major discovery where they've chemically typed it to the Mississippian, and the Mississippian gets richer and thicker westward. So the farther west we go, the more chance we get to have oil. The Cretaceous severe orogeny, which created the big mountain belt out in western Utah, shed sediments back toward Colorado. And as you go eastward, you get deeper and deeper water, and you start picking up more of the shales that have the oil, the organic material in. As you go westward, you're starting to come back up onto that pre-existing mountain in western Utah that's gone now. It's all eroded off, and you don't have any source rock there. So it's very similar to the Antler orogeny, where we have the big mountain over in central Nevada. Out in front of that mountain, you have the floodplains, the Portland Basin. That's where the richest source rocks are deposited, and that's and this is the very eastern edge of that Portland Basin. Is this new billion-barrel discovery.
We're out here in Railroad Valley. This is where they found the first oil fields in Nevada. This Eagle Spring field, Shell found it in 1954. That's the first commercial oil seep. They found it right below the tertiary unconformity. What we have out here are these, most places in the world where you have thrust belts, you have oil seeps that bubble to the surface. But out here in Nevada, the oil seeps were sealed in by tertiary volcanic rocks. And that was about 30 or 40 million years ago, and after 30 or 40 million years, these oil seeps have built up enough oil to become commercial oil fields, like Eagle Spring Field. In 1975, they found the Strat Spring oil field. They actually found the oil's being produced out of the basal volcanic rocks, out of tuffs. And then we have the prolific Grant Canyon field, just below the tertiary conformity. That's where these karsted Simonson dolomite, Devonian Simonson dolomite, has flowed 4,000 barrels a day for 10 years. That's another commercial oil seep. So these commercial oil seeps indicate there's oil in the system, but because the false understanding of, or the misunderstanding of the structure of the Nevada, people didn't bother to look at the great big fault folds where this oil is coming from. They've been looking out here in the synclines and not getting up on top of the great big fault folds, which we're doing here with the Eden Project. Now the Eden Project is just 50 miles due north of here, along strike, and so we have oil in the system here. Just northwest of the Eden Project, we have some more commercial oil seeps. So Eden Project is actually between two producing regions in Nevada, a great big anticlinal system between the commercial oil seeps, as we have here in Railroad Valley. There's very few places in eastern Nevada where you have east-west exposure of the thrust belt, but the Tempe-Hoot Range, because of headwood erosion of the Colorado River, has dug out this all the cover off the top of it. The volcanic rocks and the valley fill has been dug off the top of the Paleozoic rocks, so we can see a continuous east-west exposure. And we can see a continuous east-west exposure. Instead of finding all those Horst and Graben normal faulting that's been published for years and years, what we find are many, many thrust sheets through the Tempe-Hoot Range, and it gives us a very good structural model of the entire Great Basin. We're here in the Paw Rock Range, which is the eastern part of the Tempaiute transect. We're standing here at the top of the Simonson Dolomite, which is a middle Devonian. It's just below a major unconformity. We have an unconformity just above this contact separating the Guillemette Formation, which is upper Devonian, which is predominantly limestone, from these rocks below the unconformity, which are pervasively dolomitized. This is our main target at the Enoa anticline. They're 200 to 400 feet thick. The core at Grand Canyon looks identical to these rocks we're looking at right here. And so this is our main target up in the Enoa project.
Underneath that, these low slopes over here, that's your Mississippian shales coming underneath all these Devonian carbonate rocks. So you get your reservoir on top of your source rocks right here. Absolutely perfect what you want for oil and gas.
Right over here, the bed's screaming down to the east right there, and boy, you just picture that, how the thing rolls way up and over, and huge anticlinal system. In this structure we have about 9,000 feet of Mississippian shales and sandstone as a seal. Then below that we have Devonian carbonate, which is our main target. And then below that we have subthrust Mississippian shales. And the reason we know it's subthrust is due north of us, behind us, about 5 miles, we have the Exxon Aspen well, where they drilled down through the Mississippian, through the Devonian carbonates, and into the Mississippian source rock shales below it. It's a giant Saudi Arabian-sized structure we're standing on. And what we want to do is drill at the culmination of this anticline, which will be down here in the valley. We'll save 4,000 or 5,000 feet of drilling. And as we drill down, we may have production as shallow as 6,000 feet. Our main target will be down several thousand feet below that. Here we're at the north end of the Grant Range, between the Grant Range and the White Pine Range. And one of the evidences of thrusting is you can see the offset of here's the Cambrian Ordovician contact right here, and it's been offset by a right lat or a strike slip fault in the hanging wall. But when you look into the footwall, which is out here, that fault does not continue through. It's not broken by this strike slip fault. So that thing's is evidence of you have sliding within the hanging wall plate, but the footwall plate has not been involved in this strike slip fault. So here's a very strong evidence of this thrusting that we're looking at here near Railroad Valley. Now in Railroad Valley, the practice was, before the early 1980s, was to drill just a tertiary valley fill. So all the production in Nevada is really produced right at the tertiary valley fill between 6,000 and 8,000 feet. And most people didn't want to drill into the Paleozoic rocks because you lose circulation, and it cost a lot of money, until they accidentally drilled into the reservoir at Grand Canyon.
This is a thrust clipper, and this is identical. We find that this is the production at Grand Canyon. It looks just like this. This is the Grand Canyon structure right here. This is a model. There's only two places in Nevada where you get this big, long east-west transect. One here and one down by the Tempaiute Range. In fact, you got some little splay thrust right down in here. We got some divergent beds, some real steep, some coming in lower angle, so that's your
We're here at the north end of the Silverado Mountain and the south end of the Eden Project. We're in the Guillemette Formation, the upper Devonian Guillemette Formation, which is, you can see that it's been compressed. It was mapped by the USGS as an anticlinal system, but what we really have in reality, instead of anticline, we have an overturned syncline. And what we're seeing down here in the canyon wall here, we can see divergent beds. Here we have horizontal beds. As you look up, you can see the beds roll over. So we have a whole series of imbricate thrusts cutting through this section, and a great big footwall syncline instead of an anticline that's mapped by the USGS. They did a detailed quad map in here and completely missed the geology. Well, that's one of the reasons why we have an advantage over the major oil companies, because they relied on federal mapping, which is extremely poor, as we can see in this outcrop and most outcrops here in Nevada. The USGS got about 10 or 20% of the Paleozoic rocks mapped correctly, meaning the rest of it's mismapped. And by having the right geologic model, we can have a better model on how to identify where to explore for oil and have a better chance of finding oil. We can reduce our exploration risk. This is the Eden project, starting up here to the north and going 50 miles along strike to the south. It's an anticline. It's about 50 miles long, about 6 miles wide. We know we have a major thrust out in front of it because of the major change in stratigraphy between here and out in the valley to the east. We also know we have very rich source rocks coming in underneath, and the footwall coming in underneath this big structure. We know there's folding and thrusting up in here. We can see overturned beds and all kinds of folding and thrusting, so we know this thing's been under compression. And what we want to do is use gravity data, identify the highest culminations along this, and pick some drilling targets to drill this Eden project. We're looking at an aeromag map of the Eden project. It goes from here all the way up through here. These are 6 mile township lines. We want to notice is on the, also for orientation, here's the Exxon well that's drilled on that intrusive. As we come back here, there's a well drilling here, and then we have oil production out in here. This is the Blackburn oil field. And the important thing about this aeromag map on the Eden project is that the magnetics show that we have actually aeromag low instead of a high. If it's Horst and Grabens like the North Sea, where you have extension or a rifting, this should be a screaming high, and yet it's a magnetic low, showing the basement has not been involved, so it indicates we probably have thin-skin thrusting. The other thing to notice, there's very little chance of intrusives along here, except for one little exception right up in here. But we have the aeromagnetics show there's probably no chance of getting the rocks intruded by an intrusive, as with the Exxon problem they had over here. We do have some lava flows that came out into the valley, and that's why it's a little bit high here. What we want to do now is compare this aeromag anomaly with the gravity anomaly. So this is a gravity map of the Eden project, showing it's a great big gravity high, in contrast with Diamond Valley out here to the west, and Newark Valley out here to the east. As we go north up here, here's the Exxon well is drilled out here off the high. There's a little bit of a subtle high in here. Here's the Fasken well that's drilled up on that high, and here's the commercial oil seeps drilled out here in the gravity low. And the gravity data indicates the change in density in the area. Below the unconformity between the middle and upper Devonian, all the rocks are pervasively dolomitized. Dolomite with the magnesium ions is a higher density, and so therefore when you fold these higher density rocks closer to the surface, you're going to get a gravity high. When you take these higher density rocks and fold them down into a syncline, you're going to get a gravity low. So this indicates we have a major gravity high right in here. Also, we know we have a major leading edge of a thrust fault right in here. So this is the great big fault fold that we want to explore. And using gravity data, we can identify drilling targets that we can zero in on to drill our wells. They used gravity data up in Canada back in the 30s and 40s. That's how they found the Turner Valley field and the Waterton field. And we're just using an elephant gun out here, like you used elephant guns up there, using gravity data to find our elephants. There's also another gravity high out here, but remember the richest source rocks are coming in under this range. We don't have any evidence of rich source rocks coming in under this gravity high over here. So we want to drill where we have the least risk. We know there's good source rocks coming in underneath that thrust fault fold right there. Right along strike with the Eden project, we have the Exxon well that drilled down through the Mississippian, went through Devonian, and then went back into several thousand feet of Mississippian rocks. They proved the thrust model, so we know there's got to be thrusting all the way underneath all this area here. A little bit to the west of the Exxon well, there's currently a well drilling right now up here on by Fasken Oil at Bruffy Basin. And Bruffy Basin is another part of another large anticlinal system, very similar to the Diamond Range. And then a little bit farther west, we have some more of these commercial oil seeps that show there's oil in the system, very, very close to the northern end of the Eden project. All right, here we are at the Fasken Well, which is about 15 miles northwest of the Eaton project. The well here, we're going to be going through the Devonian hanging wall, back in the Mississippian footwall, then into the subthrust Devonian. The Eaton project will be very similar. We'll be going through a hanging wall plate, and we want to find a structure below the hanging wall, which is sealed in by Mississippian shales, and that'll be the Eaton project. This is just a single prospect here. The Eaton project may have as many as a dozen prospects along the structure. Here we are on the south end of the Eaton project, up on Newark Mountain. We're standing in the Devonian Gilmet Formation, and we have, you can look over here and see several thousand feet of Gilmet Formation. These layers over here, these are mostly limestones. Below that, we have a major unconformity between the Gilmet Formation and the Middle Devonian Simons Formation. It's a regional unconformity, and below that unconformity, the rocks are pervasively dolomitized. In other words, the carbonates have been, the calcium carbonate has been replaced with magnesium carbonate, creating better porosity. And also below this unconformity regionally, we have a karst zone of 200 to 400 feet thick, that when we drill into it, sometimes we get bit drops. This is the same karsted zone that's producing out in Railroad Valley, which is along strike to the south of us. In the footwall of this structure, out in the valley down below this Newark Mountain, we'll have Mississippian source rocks acting as a seal, also as a source rock. And what we want to do is get down, find this in the highest structural culmination, and drill into those into the footwall, drill through the Mississippian shales, which will be a seal on top of the hydrocarbons, and drill on into the footwall Devonian carbonates. And that's where we think we'll find some major oil reserves. Also interbedded with the shales, we have some sandstones. So that gives you the entire stratigraphic sequence here, all in one big, huge anticlinal fault fold. And underneath this fault fold, we have repeated Mississippian source rocks and seals, and then we have it again. So it's a duplex system, a giant duplex system here with a potential of giant oil and gas fields. All 50 million barrels of oil that's been produced in Nevada and the new billion-barrel field in central Utah are sourced from the Mississippian source rocks. Back during the Mississippian time, or late Devonian or late Mississippian time, we had the antler orogeny here in central Nevada that shed sediments back toward the craton, and the richest source rocks are deposited right here in front of the antler orogeny here. And the very richest rocks are here, and they get leaner as you go over toward central Utah. Okay, this is an isopac map of the Mississippian siliciclastics of western Utah and eastern Nevada. And we see a zero line over here in eastern Utah, where all the Mississippian rocks are carbonates back this way. And as you come this direction, you pick up some shales and sandstones, eventually some conglomerates. You get up to 9,000 feet over here in central Nevada. Over here we have the new Richfield discovery, where the source rocks are very, very thin. Very few source rocks that created that billion-barrel field here, but they get much richer and much thicker back this direction. Here we have a large stratigraphic wedge sticking in here toward Salt Lake City. This is part of the Precambrian allocogen that parallels the present-day Uinta Basin. And I call this the Proto-Ochre Basin during Mississippian time. Later in Pennsylvania, that opened up and became the Ochre Basin. And so we have this big wedge sticking in here. But the very best source rocks are deposited right over here where the rocks are the thickest. Here's the oil production here in Nevada, Nye County, and there's production up here in Eureka County up in here. Okay, this is the depositional models of the Antler Basin. The top one here is published by the United States Geological Survey, where they recognized the antler orogeny over here. They had deep flished turbidites. They said all these siliciclastics come in by deep water sedimentary bypassing. All this is super deep water. I did my master's thesis on this at unit right in here, and this is the model I came up with. Instead of saying all deep water flished turbidites, I recognized there was marine, non-marine, marine, and non-marine. And if we use Exxon's new vernacular, we'd call that transgressive and regressive sequences. And the evidence of the non-marine regressive sequences, which is in green here, interbedded with the marine, is found, the best evidence is found over in the Ochre Mountains. In the southern Ochre Mountains, there's a clay bed where the footwall of this clay bed, we have terrestrial plants at the transgressive sequence boundary, and then we have non-marine shells through the rest of the sequence here, and then we have a transgressive sequence boundary over the top with a rip-up class from the underlying sequence. So it's a classic sequence stratigraphy, and let's go and look at these fossil plants that form the basal part of that sequence. We find in the basal part of that sequence boundary, we see these terrestrial plants with rootlets. These little lines coming off here, these are rootlets that penetrate the bedding planes. It's absolute evidence that this is non-marine. You can't grow vascular plants in a marine environment. So these are lacustrine rocks. The rootlets come off at 360 degrees. They come off in whorls around the root. The layer above that, you find the trunks of the trees. Here's the lepidodendron trunk here. There's another species of lepidodendron here. And also within the clays, interbedded with these roots and trunks, we find clays with microscopic spores. And the assemblage of spores we find here, or in many places we find, are 100% lacustrine or non-marine. So it's a very strong evidence of non-marine deposition. So the main source rock in Nevada is not marine shells, but it's non-marine lacustrine oil shells. Some people would argue that we may have had some islands out in the USGS deep Flysch turbidite basin, but here's where I found the terrestrial plants over in my master's thesis area. But this is the area where we find the terrestrial plants in place. In other words, it's the entire Foreland Basin here. There is no Flysch turbidites as published by the USGS, but it's most of it's lacustrine beds. And again, these are the richest oil source rocks, and they become much richer over here in central Nevada. Because we have the biostratigraphy from the polynomorphs, those microscopic spores, we can do time slices now through the Antler Basin and show how the source rocks stack up through time. So here we start in the early Mississippian, the Kinder Herkian, early Merrimack. We see the richest source rocks are distributed right through this part of central Nevada. A few million years later, again, the lake beds are in the very same place again, where we have the lake beds right through here with the richest source rocks. They become leaner out this way. Millions of years later, the source rocks are still stacking up in the same place. So now we're getting thousands of feet over millions of years stacking up in the very same place in central Nevada. We're up in the late Chesterian. Again, the lake beds are right through here. We have some large barrier sandstones with nice porosity in these sandstones. Could be some interbeds of sands for reservoir rock within the Mississippian. Then we move up into the latest Mississippian to early Pennsylvanian. We actually have a big delta system working its way over into the Uinta Mountains of Utah, over past Salt Lake City here. And the richest source rocks, again, are just deposited right through here. And so over millions of years, we get the same area where we have the lacustrine source rocks stacking up. We get out on the outcrop and see what the source rocks look like. They were so rich up in central Nevada that during the 1800s, old timers, the old miners, mined these lacustrine oil shells for coal. Some places are so rich you can actually ignite them. They're actually ignitable. I took a sample of the Cherry Creek coal mine here, and the organic richness run as much as 89% total organic content. In some places you can break ammonoids open within these shells. It's so rich you can get live green oil coming out of the ammonoids on the outcrop, as seen in the photograph here. We get a lot of oil coming up through springs. You see these oil globules coming up through the springs up here and up near the Eden Project. After Cedar Strat had collected thousands of samples, the major oil companies had asked Cedar Strat to do this work for them, asked me to put together a regional source rock study. This is one of the figures out of that study showing the organic, average organic content. And you can see that the average organic content is very, very rich over here towards central Nevada. In comparison with that new discovery over here in central Utah, here it's less than 1%, and here the average over here in central Nevada is up to 5 and 6%. Now the Eden Project is located right up in here in the Diamond Range, right along the very richest source rocks. Here's Railroad Valley down here, and here's Eureka County up here, and right through here is the Eden Project. Also the maturation, this is on the vitrinite reflectance, how hot the rocks have been cooked through time. This shows that the Mississippian source rocks are at the peak oil generating window based on vitrinite reflectance. And based on Mississippian conodont alteration indices, again this area right through here in central Nevada shows the Mississippian source rocks are at the peak oil generating window, same as with this Richville deposit. These areas out in here that's in red, that would be in the gas window, and these areas out in here, these purple areas would be beyond the gas window, the oil has been burned out of it. So in kind of summary, this is all the maturation indicators all put together. Here's the Diamond project, the Eden NOAA project right through here. It's a clip of over-mature rocks sitting in a sea of rocks at the peak oil generating window. So we drill through the hanging wall plate and we'll get back into these rocks within the peak oil generating window here at in the Eden project. There's only several places in the eastern Great Basin we have a continuous east-west exposure. The Tippahut Range down here towards southern Nevada is a place we have almost 40 miles of continuous east-west exposure of the Paleozoic rocks, where we have enough headward erosion from the Colorado River to dig off the valley fill and the volcanic rocks so we can expose these Paleozoic rocks. And so when we do a cross-section through the Tippahut Range, this is what the cross-section looks like. It's instead of a bunch of horse and grobs, we actually have a major thrust belt through here. And we want to do now is compare the Devonian stratigraphy from here, here, and here, and then restore this thrusting and see if it makes stratigraphic sense. As we compare the three sections of the Tippahut Range from the east to the west, this is a Devonian stratigraphy with a surface gamma ray log. We've broken out the Devonian sequence into 21 mappable sequences. We want to do is compare the stratigraphy, what happened right above this sequence here. This is a sequence created by a meteorite impact that dug up the seafloor, and we've got up to 400 feet of impact breccia, and we want to see what happened right on top of that impact breccia in this impact crater down here in southern Nevada. Here's the impact breccia right here. This is what it looks up close up. You see these big chunks of limestone and a gray dolomite matrix. Here's another shot of the breccia. You can see the Devonian cycles down here. They're interrupted by the impact breccia event. Then you go back into normal depositional cycles. Here we have one 200-foot graded bed. The clasts down here at the bottom are thousands of feet long. Here's a telephoto shot of this clast right here. You can see the brittle carbonate rocks are folded up. You have boulder-sized cobbles in here, you have pebbles, and then you get up to sand size and silt size. Time you get to the top of this breccia, you have iridium anomalies and shock quartz and all the other indicators of impact breccia. Okay, what we're going to see now is what happened, what was deposited right on top of the breccia. Over on the east side of the range, we have the impact breccia with this lens-shaped 200-foot reef. We move over to the next thrust sheet to the west. Above the breccia, we have, here's the impact breccia, we have shallow water sandstones deposited above the breccia. Now we're going to take our helicopter, we're going to fly out here to the next range to the west there and see what's above the breccia on the very western edge of this Tippahut transect. And here we have deep water ribbon limestones lying on top of the breccia. Here's all three sequences put together. Here's the deep water ribbon limestones over here. Here's the shallow water sandstones here. And over here we have the reef on top of the breccia. Now what we're going to do, we're going to pull this thrust back by thrust reconstruction using Exxon snip reconstruction method. When you pull that back, you have to pull this back about 50 miles if you honor the bed lengths. When you do that, you have the shallow water sandstones over here. You have your deep water ribbon limestones deposited in the impact crater, and then you come back up onto to the east edge of the crater. You have your reefs that were deposited on the east edge of that impact crater. Here's a distribution of the impact breccia. Right now, at present day distribution, you have two bullseyes, and then when we pull the thrusting out of it and re-isopack it, here we get almost a perfect concentric impact crater. So what that does is it gives us a tool now as we compare the present day with a restored impact crater. what we have now is a tool to tell us how far back to pull the thrust sheet. So once we pull the thrust sheets back perfectly in the perfect position, this impact crater will become perfectly concentric. Okay, and we was talking about this area right down here. If you take all 21 sequences of the Devonian, you have this big oblong-looking basin, and then if you pull all the thrusting out beyond the the Timpahoot range here, you'll have a basin about the same dimensions as a Williston Basin, only with a thrust fault going right through the middle of it. And right through the middle of this thrusted Devonian Basin is where you find all the oil in Nevada so far. And the Eden project is right here.